Hello, Hire. Today's lesson is on bond enthalpy, and this is part 2 of the chemical energy subtopic, which is found in Unit 3, which is Chemistry and Society. Our learning intention for today is to investigate what is meant by bond enthalpy and to learn a method for calculating enthalpy changes using bond enthalpies. So what we want to be able to do by the end of this lesson is to define both bond enthalpy and mean bond enthalpy, which mean two different things, and to complete some bond enthalpy calculations based on data that we're given either in the question or we might need to find it in the data booklet. So first of all, what actually is bond enthalpy? Well, it's the energy required to break 1 mole of chemical bonds in the gaseous state to form 2 moles of gaseous atoms. So for example, here we have XY as a compound with a bond in the middle. Remember, everything has to be gases. So this here is being broken into 2 individual moles of atoms. Now for diatomic molecules like HCl or H2, there's only 1 bond energy since that bond only exists in that molecule. So your HCl bond is always going to be within an HCl molecule. Your H2 bond is always going to be within an H2. Any of your diatomic elements like iodine, bromine, chlorine, this is true for. Something like carbon to carbon, though, can exist in a variety of different molecules. So you can have a carbon to carbon bond in an alkane, and an alkene, a cycloalkane, an alcohol, a carboxylic acid. There's lots and lots of different molecules where it might appear, and this is why the data booklet gives bond enthalpies for diatomic molecules, but mean bond enthalpies for the case of carbon to carbon and others like it. The mean bond enthalpy is basically just kind of an average of all of those different energies of where it appears in different molecules, and we can use the mean bond enthalpy for whichever example we are looking at. So the easiest way to kind of to learn how to do these calculations is just to talk through the method for each of them and then do lots of practice. So the question would say something like the mean bond enthalpy for the OH bond is given as 463 kilojoules per mole. So it's given us this here, we're not having to use the data booklet this time. And it says delta H for the reaction can be found using this method. So a question would ask you to calculate the enthalpy change using bond enthalpies. So we have H2O, remember everything is a gas, and on the left we have delta H positive. Now this is because when we break bonds we have to put energy in to break them down. Think about a water molecule as a molymod. If you have to take that molymod apart into little bits and break up the bonds, you're having to put your own energy into it to do that. Bond making is the opposite. When bonds come together, they release energy. So that's why we have delta H negative. That's an exothermic process. And as we know, the enthalpy change for exothermic processes is negative. So on the left, you always have bonds breaking, which is delta H positive. And on the right, we always have bond making, which is delta H negative. So how do we actually calculate the overall enthalpy change? Well, what we need to do is we need to think about what compounds we have on the left and the right, where the bonds are, and how much each bond is worth. So if we start by drawing a water molecule, so we have an O with 2 H's, that means that we have 2 oxygen to hydrogen bonds. So here's number 1 and here's number 2. Now what we have to do is we have to find out, well, how much does that represent in enthalpy? And the question tells us that each OH bond is worth 463 kilojoules per mole. We happen to have 2 bonds, so that means we need to do 400 and 63 times 2. And that comes out at, if you've got a calculator handy, 463 times 2, 926. So that would be our positive value, our delta H positive. On the other side, we don't actually have any bonds in this. We have 2 hydrogen atoms and 1 oxygen atom. So there are actually no bonds being made on this side. So we don't actually have a negative value in this example. When we come to calculate the total delta H for the reaction, all we do is add these two values together. So because we've got a 0 on this side, we're just left with positive 926. I always just out of habit write the positive sign, but you don't actually have to in the marking scheme if you just write 926 kilojoules per mole. They will assume that you mean positive. If you do end up with something that is a negative value, though, you should include the negative value. So that is how we carry these out. Let's do another couple of worked examples using the same method and see if we can do some questions at the end. Just remember something very, very important. Try and not mix up the bond breaking and bond making enthalpies. Remember that bond breaking is delta H positive because energy has to be put in, which is endothermic, whereas bonds forming releases energy and that's exothermic, so delta H is negative. If you ever get stuck, I always just think about molemods. Breaking up molemods requires energy. Breaking up bonds requires energy, and bonds forming releases energy. So, worked example 2 then, this is an actual question we're going to work through together. Calculate the enthalpy change in the following reaction using bond enthalpy data from the data booklet. So we're going to have to look our values up this time. If you have a data booklet handy in front of you, it is page 10 you're looking at. So step 1 in a situation like this, we are not given the full structural formula for these molecules. So what we have to do is we have to draw them. This should not be difficult for anybody because this is National 5 knowledge. You should know what alkanes look like. So step 1 is to draw all of that out. I've done that already. So we've got a chlorine molecule, an ethane molecule, and then we've got 1 chloroethane and HCl. Step 2 is to circle all of the bonds on the left and all of the bonds on the right. And the reason that we do this is just to keep track of how many bonds we are counting. And it comes in really, really handy when we're writing them all down. So we've got 1 chlorine to chlorine bond, which is here. We have 1, 2, 3, 4, 5, 6 carbon to hydrogen bonds. Don't forget your carbon to carbon bond in the middle. On the other side, we have a carbon to carbon bond in the middle, 5 carbon to hydrogen bonds, 2, 3, 4, 5, and our last one is a carbon to chlorine bond. We also have a hydrogen to chlorine bond on the right hand side as well. So once we have all of these highlighted, our next step is to then write down all the values. So what we do is just take each one in turn and just list them on the correct side of the equation. So remember, on the left is bond breaking, so it is positive, it's endothermic. On the right is bond making, which is negative and is exothermic. So add up all of the values and you get something that looks like this. I always keep all of the bonds that are being broken on the left and the bonds that are being made on the right, just to separate them entirely. So our chlorine to chlorine is 243. Our 6 carbon to hydrogens is 2,472. If you look up the carbon to hydrogen bond, it's 412. You just multiply that value by 6. And lastly, we've got a carbon to carbon, which is 348. Our total on the positive side then is just these numbers added up, which is 3,063. If we go to our other side, I've done the exact same thing. The only difference is this time each number has a negative. So an HCl bond is 432. If it's on the bond making side, then it's negative 432. Carbon to a chlorine is 338. Carbon to carbon, like the other side, is 348, but it's got a negative this time. And 5 carbon to hydrogens is minus 2060. So that gives us a total value of negative 3178. So to get the answer to this question, which is the total enthalpy change, all we have to do is add these values together. So 363, take away 3063, take away 3178 will give us a value of negative 115, and the units are always kilojoules per mole. If you are given the units in the question, remember, if you don't write them, you won't be penalised. If you write your units and they are correct at all times, again, you'll get the correct marks. If you, however, don't know the units and you write the wrong units, you will be penalised for 1 mark in each paper. So just be careful. Okay, example 3, again, calculate the enthalpy change in the following reaction using bond enthalpy data from the data booklet. So we're not being given any data here, they want us to go and find it ourselves. We follow the exact same steps. So step 1 is to draw out the structural formula for each molecule. Again, this is National 5 knowledge, so it looks like that. Remember, your oxygens have a double bond between them. You have your methane molecule, your 2 oxygen molecules, a carbon dioxide, and 2 water molecules. Again, what we're going to do is we're going to circle all of the bonds on the left and all of the bonds on the right so that we can keep track of them. So we have 4 carbon to hydrogen bonds on our methane. We have 2 double bonds between our oxygens. And then on the right hand side, we have 2 carbon to oxygen double bonds and 4 oxygen to hydrogen bonds on our 2 water molecules. So now we've got a wee list of all of the different bonds. Remember, left is positive, bond breaking, right is negative, bond making. So if we go to that little list and add up all the values, we get this. So 4 carbon to hydrogens is 4 multiplied by 412, and we get 1648. 2 oxygens, if you just look that up in the data booklet, that's on the bond enthalpy side, the left hand side, it's 498 times 2, which is 996. That means our total on the left is positive 2644. On the right hand side, this is our negative side, remember, we have 2 carbon to oxygen with a double bond, and that gives us a total of 1486. We have 4 OH bonds, and that gives us a total of negative 1852. Our total negative value is negative 3338. So as always, step 4, to get the enthalpy change for the whole reaction, all we have to do is add these values together to get 2644, take away 3338, and our answer is negative 694 kilojoules per mole. So as you can see, every time you answer these questions, you just do the 4 steps in that order. Make sure you double check all of your numbers and all of your bonds, and you should always come out with the correct answer. So what we're going to do now is we're going to attempt to do some questions on bond enthalpy just to make sure that we understand the concept. As always, if you would like to, you should try and complete the questions before we go over the answers to make sure that you're kind of trying to figure it out yourself, and then self-mark when we go over the answers. So question number 1 says the mean bond enthalpy of a carbon to fluorine bond is 484 kilojoules per mole. And which of the processes is delta H approximately equal to plus 1936 kilojoules per mole? So how do we figure this out? This is quite a kind of problem solving based one. But if we look up, or it tells us in the question actually, that the carbon to fluorine bond is 484, If you multiply 484 by 4, you get that number, 1936. So what that means is that on the positive side, or the bond breaking side, we're going to be breaking 4 of those carbon to fluorine bonds. So that means that we should have a CF4 molecule on the left. What doesn't help us is the fact that every single one of these does. But if we understand our bond enthalpy calculations, that means on the right hand side there can be no bonds being made, because if we've already got our 1936 on the left from breaking down those 4 carbon to fluorine bonds, if there were any bonds on the right to be broken, that would then take away from that number, which we don't want. We want it to equal 1936. So what we need to look for is an option where on the right hand side no bonds are being made. Now, there are a few wee other things to look out for. There is carbon as a solid here and carbon as a solid here. Now, remember, when we're working with bond enthalpies, everything is a gas. So you can immediately discount A and D because solids do not count in these calculations at all. In C, we've got 2 fluorine molecules. If the fluorines are together in molecules, then that's going to include bonds, which we don't want. So our answer that we are looking for is going to be B, because we have carbon by itself as a gas and 4 fluorine atoms by themselves as a gas. So that means we only have bonds being broken, we don't have any bonds being made, and 4 of those bonds adds up to the number that we are looking for. So those can be quite tricky, but if you just kind of try and use your logic, if you want to doodle and draw what the carbon tetrafluorine looks like, so you have an idea that's 4 bonds and the 4 bonds add up to this number, then that's fine. But as always, you can always discount the ones with solids as well, and if you're really struggling, kind of try and make an educated guess. But the answer to this is B, and that would be worth 1 mark. Number 2, methanol can be converted to methanal as shown, so we're actually given the full structural formula this time, which is quite nice. Using bond enthalpy and mean bond enthalpy values from the data booklet, we have to calculate the enthalpy change in kilojoules per mole for the reaction. So step 1, drawing out the formula, has already been done for us, so we're going to go straight ahead to the second step, which is to circle all of the bonds that we're interested in. So let's do that just now. So we have 1, 2, 3 carbon to H's, 3 carbon to H's, and we have 1 C to O, and we also have 1 O to H. So that is our bond breaking side. We're now going to do our bond making side. So we have 2 carbon to hydrogens, and we have 1 carbon double bond to an oxygen. And lastly, we have the hydrogen to hydrogen bonds. We have 1 hydrogen to hydrogen. Now what we need to do now is fill in the numbers for each side. Remember, we make the left numbers positive and the right numbers negative. So our carbon to hydrogen bond is 412. If we multiply 412 times 3, now remember, we're getting these values from page 10 of the data booklet, then we get 1, 2, 3, 6. So we have 1, 2, 3, 6. A carbon to oxygen bond is worth 360. And an oxygen to hydrogen bond is worth 463. That looks like 465, but it's meant to be a 3. On the right hand side, remember, we have negative numbers. These bonds are forming, so we're getting energy released. So Again, carbon to hydrogen is 412, multiplied by 2 gives us 824. We're going to have negative 824 for that. A carbon double bond oxygen is 743, so we've got negative 743. And a hydrogen to hydrogen, we have 436. 436 with a negative. So what we do now is add up all of our values on both sides. So on the left-hand side, if you've added them up correctly, you should have 2059. On the right-hand side, you should have negative 2003. And when you add those two together, you should have 56. So the total change in enthalpy, now obviously you can write all that out, I just have limited space, is plus 56. And the units are kilojoules per mole, remember. It does give you that in the question though, so you wouldn't have to write that, you would get the marks for writing plus 56. So that was a kind one where we were given the structural formula. They're not all like that, but you will find that sometimes they will do that. And that would be worth 2 marks. 2 marks these questions are usually worth. Again, here we've been given all of the structural formulas, so it's quite a nice question. The alkynes are a homologous family of hydrocarbons. The simplest member is ethane, which is C2H2, and it's used in welding torches. And it gives you the formula there, the structural formula. Using bond enthalpies and mean bond enthalpies from the data booklet, we have to calculate the enthalpy change in kilojoules per mole for this reaction. Again, step 1 is to draw out the full structural formula. We've done that, so that's good. Step 2 is then to circle the bonds on both sides. So let's go ahead and do that again. And try and come up with a little list of the substances that we're going to be looking for. So straight off the bat, I can see we've got 6 C to H's and 1 C to C. Now, I have kind of limited space here, so I'm not going to write it all out. I'll just tell you as I go and then write it at the end. So you've got 6 carbon to hydrogen bonds and 1 carbon to carbon bond on the left. That's our positives because we are inputting energy to break the bonds. The bond making step, we have 2 carbon to hydrogens and we also have a triple carbon to carbon bond. And then we have 2 hydrogens on the right as well. So values for these then, since you're hopefully already done these and you're self-marking. So what you should have is for your carbon to hydrogen, we have 412 times 6, which is 2,472, plus our carbon to carbon bond is 348. That gives us a total of 2,820 for our positive side. Our negative side, we have a carbon to carbon triple bond, gives us a value of 838. Remember, on the right hand side, this is our negative side because the bonds are forming. So we have negative 838. Our carbon to hydrogen is going to be 412 times 2. And then we add our hydrogen to hydrogen, which is 436 times 2. Remember, all of these values are negative. We end up with minus 2,534. So when we do our total, our delta H for the whole reaction, we have 2,820 minus 2,534, and that is going to give us out 286. Units are, of course, kilojoules per mole. They are given in the question. So 286 we get for that. Let's try another example. This is another multiple choice question. You'll find that in the multiple choice questions, they usually do give you the bond enthalpies, so it just makes the process a little bit quicker so that you don't have to go and look them up all the time. So we have H2 and Br2 on the left and 2 HBr on the right. Now these are quite simple structural formulas. We know that a hydrogen molecule looks like this, a bromine molecule looks like this, and we have an HBr that looks like that. So our bonds broken are these two here. They're going to be positive, so we're going to have a 436 plus 194. So let's go ahead and do that in our calculator right now. So 436 plus 194. That gives us a total of 630. Now our negative, our bonds being made, are two hydrogen bromides, which are 366 each. So we're going to be taking away 2 times 366. That is going to give us a value of negative 102, which happens to be our value for A. So the multiple choice questions are quite straightforward, especially when they're laid out like this, when they tell you what's been broken and tell you what's been made. The real knowledge that they're testing here is, do you know that bonds broken are positive and bonds made are negative? That's what they're looking for. Question 5. The combustion reactions of methane and heptane can be studied in different ways. The combustion of methane produces carbon dioxide and water vapour when carried out at temperatures above 100 degrees C. So we're given an equation here. We're not given the full structural formula this time. So this is something that you're going to need to write out by yourself. Using bond enthalpies and mean bond enthalpies from the data booklet, calculate the enthalpy change in kilojoules per mole for this reaction. So as always, it looks exactly the same as every other question layout is, and we're going to follow all of the steps as usual. So if you are hopefully self-marking, you'll know that methane is CH4. Our oxygen molecules are, we've got 2 of them, and they are oxygen atoms with a double bond between them. On the other side, we have CO2 with our C in the middle and 2 double bonds to 2 oxygens. And then we have 2 water molecules. So our list on our positive side is going to be as follows. Your carbon to hydrogen bond, you have 4 of. I feel like I should maybe write this down. Hopefully it'll let me. Your carbon to hydrogen, you have 4. And that is going to equal 412 times 4, which is 1,648. I would always draw, if I had space, I would draw this out. Like every time you get a question, if the full structural formula isn't written for you, you should always draw it out. If you try and do it just from the molecular formula, the chances are you'll make a mistake and get it wrong. The next one is we have 2 oxygen to oxygens. And that is going to give us 498 times 2, which is 996. So that's our bonds that are being broken. Our bonds that are being made, we've got 2 carbon to double bond oxygens, and that's going to equal 743 times 2. But remember, it has a negative, so we're going to have negative 1486. That does not look like 1486, but that's what it's supposed to be. And then our oxygen to hydrogen times 4 is going to be 463 times 4. So we have negative 1852. If you add those up correctly, you should end up with 2,644 on the left for our positive number. On the right hand side, we've got negative 3,338. That gives you a total, when you add them together, of negative 694. Delta H for the total reaction is negative 694, and we have kilojoules per mole as our units. Okay, so again, exact same process. You would write this out fully on your paper so that you can circle all your bonds. Make a list of positive values on the left and negative values on the right, and then at the end you just add them together and you come out with your total enthalpy change for the reaction. The last question here is about the difference between bond enthalpy and mean bond enthalpy. And what you would need to say for this question to get the marks is that bond enthalpy is talking about a specific bond that only happens in that molecule, like hydrogen to hydrogen, oxygen to oxygen, HCl, any of the diatomic elements you could mention for that. Mean bond enthalpy is something that could exist in many different molecules, like a carbon to carbon single bond, a carbon to carbon double bond, an OH bond, a CO bond. These bonds appear in many, many different molecules, so it'd be hard to pinpoint an exact energy. Therefore, mean bond enthalpy is what it sounds like. It is the average bond enthalpy for all of those different molecules that the bond can exist in. So something along those lines where you say that bond enthalpy is for a specific bond that can only happen in that molecule, whereas mean bond enthalpy comes from an average of all of the different compounds where that bond can be found. And that is this lesson finished. We wanted to be able to define bond enthalpy and mean bond enthalpy. Hopefully, if you manage to get that last question correct, then you can do that. Well done. And we wanted to be able to complete bond enthalpy calculations based on the data that we're given. Remember, if the question does not give you the bond enthalpies, these can be found on page 10 of the data booklet. If you have any questions at all about today's lesson or any of the content, then as always, you can give your teacher a wee message on Google Classroom and we'll get back to you as soon as we can. Hope you have a great week, guys.